So I thought it might just quickly be worth touching on some of these things on Osborne's rule that just came up, that if you had something in your formula like a sine cubed theta, that does have a sine squared in it, so it would be negated, and it would become a minus sine cubed theta, or whatever input. I just picked a different input. If you had something where your formula was a sine to the power of 4 theta, well, what did we say would happen, Ariful? It would actually stay the same because there's a squared and a squared, so it's negated and it's negated again, which means that it's actually just gone back to where it originally started. So it would just be replaced with a sine to the power of 4 theta. If it was a sine to the power of, a sine to the power of 6 theta, it would be negated because it would negate, not negate, and then it would negate again. So just to make that point clear. Okay, so the last thing that we need to know how to do for this topic, for the first half of chapter 6, is how to solve equations. And there's two kinds of ways of solving equations, and these things we're going to do today will strengthen your equation solving in normal maths as well, in some ways. At least it will strengthen the beginning of equation solving. So you have to decide whether to use hyperbolic identities or the definitions of the hyperbolic functions. So to start with, I'm not going to even ask you about this question. I'm going to ask you about this question. Don't know why I've put an H in there. How would you have solved this question in trig? Do we know a way of solving this equation in trig at our study point? So if we would usually try and divide everything by cos, so you'd have 6 tan x minus 2, but then you get 7 cot x. So we actually don't have the skills to be able to solve this one in trigonometry yet, okay? Yeah, I don't know why I wrote cot, sorry. So we would have been able to solve this one if it wasn't equal to 7. If it was equal to 0, then we could do that one. And if you could do it, if you can do it in a trig way, then that's going to be the way that we would try and do it with hyperbolic. But in this case, there's not an obvious way of how we would have solved it with trig, because we would have got stuck with this sec that we had previously, which wouldn't have been helpful. So what we're going to do, we're not going to use the hyperbolic identities here, because there's not going to be an identity that will help us. We're going to use the definitions of the hyperbolic functions instead, okay? And that's going to be more familiar with what we did last lesson. So when I say the definitions of the hyperbolic functions, I just mean the exponentials. So this is going to be 6 sin x. Well, that's going to be 6 over 2, which I'm just going to write as 3 e to the x minus e to the minus x. And 2 cos x is being subtracted, so I better put it in brackets. 2 times a half is 1, so I'm not writing that down. And it's e to the x plus e to the minus x equals 7. So this one, there wasn't an obvious thing to do with trigonometry here, so I'm going to use the definitions of the hyperbolic functions. I'm then going to expand everything out. So that's 3e to the x minus 3e to the minus x minus e to the x minus e to the minus x equals 7. And then I'm going to simplify that, which is 2e to the x minus 4e to the minus x minus 7 equals 0. What next? Good. This is the version of things that looks like a quadratic. So we want to make it a quadratic by multiplying it by e to the x. So we get 2e to the 2x minus 4 minus 7 e to the x. So just putting it in the standard quadratic kind of way that we have, we get this. And then I'm going to do my quadratic solver. So either e to the x is equal to 4 or e to the x is equal to minus a half. Tell me more about this. This one will have no solutions. And the reason it has no solutions is because we know that e to the x is always greater than 0. So my solution is just going to be that x is equal to ln4. Now, I'm going to just think through how I know there's only going to be one solution. You may not think in the way that my brain thinks here, but I'm going to put on the left-hand side, I'll put 6 sine x, and on the right-hand side, I'm going to do 2 cos x plus 7. And I'm going to roughly sketch this graph, and I'm going to roughly sketch this graph, just to show my brain that there's only one solution. So the left-hand side of the graph is going to be a sine graph, which looks something like that. And a 2 cos x plus 7 is just going to be some kind of graph that's like this. So they only cross in one place. So there's some logic behind knowing how many solutions there should be. And that logic is coming from knowing what the graphs look like, which is why I wanted you to know what the graphs look like. Obviously, you can use equation solvers on the calculator and stuff like that too, but I want you to become really good mathematicians, and that's how we get there. So we need one solution, and it is that x is equal to ln 4. Can I go on to the next bit? Yeah. So this time, we have this equation. 2 cos squared x minus 5 sine x equals 5. If this were trigonometry, what would you do? Yeah, if this were trigonometry, we would be annoyed that we have a mixture of cos and sine, a cos squared and sine, so we would replace the cos squared with sine squared. So we're going to do the same thing, because if we can use an identity, the equations are much quicker to solve. So we're not going to use the definitions this time. This time we are going to use the hyperbolic identity. Which hyperbolic identity are we going to use that will for this one? Good. Cos squared x minus sine squared x equals 1, which tells me that cos squared x is equal to 1 plus sine squared x. So we're going to substitute that bit of the identity in. And we get 2 brackets 1 plus sine squared x minus 5 sine x equals 5. So 2 plus 2 sine squared x minus 5 sine x equals 5, which is 2 sine squared x minus 5 sine x minus 3 equals 0. So we'll go to our quadratic, where we have 2 minus 5 and minus 3. And this gives me that either sine x equals 3 or sine x equals minus a half. Did everyone else get that? Yeah. Okay. Now for the sine graph, there's going to be a solution for both of these. Because if you think about what the sine graph looks like this. So we're trying to say, what's the value of x where sine is equal to 3? So we're going to find out this value, and the value when it's equal to minus a half. So we're going to find out this value here. Now, I want to have the exact answers for this. So how could I find out what x is equal to? There's a long way and there's a short way. Good, we're going to use the definition of r sine. That's the quick method, because actually x is equal to r sine 3, and then we have the definition of that. The long way would be replacing sine x with the definition of sine x, and then coming up with a quadratic, and it's a waste of time. So if you can flick back a few pages, can you tell me what the definition of r sine is? No, r sine x, not the reciprocal, not sec, it's the ln one. It's ln of... Is it plus? I think it's minus. Can you check, please? No, it is plus. You're right, it is plus. It's x plus the square root of x squared plus 1. Sorry, Haroon, I was telling you you're wrong and you're not wrong, okay? So if I'm trying to do r sine of 3, I can use this shortcut, and I can just say that x is equal to the ln of 3 plus root 10. It's in the formula book, and it's kind of rare that you use it, because you only use this in solving equations with hyperbolic functions, which there will be one question across 2 exam papers. Maybe not even that. This might not even come up. And then we're going to do the same for this one. So we're going to say that x is equal to r sine of minus a half So x is equal to the ln of minus a half plus the square root of minus a half squared plus 1, which is 5/4. And you could actually do a bit of work on this, which you don't have to do, but I'm going to do just to show you that there are further stages you could do if they said show that. What do you yeah, this is root 5/2, so they both have a common denominator of 2. So it's actually root 5 minus 1/2. And the ln of root 5 minus 1/2, what kind of number do you think that is? Looking at the graph. It's a negative number, because it must correspond to a negative number because it's giving us a negative value here. If this is going deeper now, okay? If I know that this is going to be a negative number, what do you know about root 5 minus 1/2? It's less than 1 and greater than 0. So it's just because ln of numbers between 0 and 1 are negative. Is it between 0 and 1? Yeah. Okay. We're not taking a natural log of a negative number. The overall, the log of this number is negative. This is not negative. This is less than 1. Okay? Is that right, that it's less than 1? I don't think it is less than 1. It is going to be less than 1. Yeah, of course it's going to be less than 1. It's root 5 minus 1/2. Yeah, it is 0.61. That's why you get, when you do ln of a number between 1 and 0, you get that. So we've got this solution and this solution that we've got here. I can't really draw what this original graph would have looked like, but my logic tells me that those are going to be the two solutions that we have. Okay. This time, I have this kind of equation. We haven't quite studied this in normal maths yet, but I think you'll be able to tell me what the issue is when I look at this equation. What's the issue with this equation? I have a double angle in here. I have different arguments, so I can't solve the equation in the way that I normally would do because the arguments of the trig functions or the hyperbolic trig functions are different. And we haven't done an awful lot of this in pure maths yet because we haven't quite got there, but you just use the double angle formulae to help you to translate it from something that is with a 2x to something that is with an x. So I'm just going to grab this double angle formula that I've got here. We are obviously going to be thinking about these ones that we have here, okay? Now, I've got a choice of the 3 versions of the double angle formula that I have. Which of these 3 choices do you think would be the best one to use and why? Yeah, I agree. Why the second one, Shahan?
Because the other term is cosh x, and if you use that one, you'll get cosh x.
Yeah, if we use this one here, the entire question would be in the same language of cosh. And I would avoid, well, actually, if I use this one, I would have to negate it, but it's still, there'd be an issue of having to use another identity. So this one is lucky. We didn't have to use the hyperbolic version. Well, we did, because the hyperbolic version is the same as the trig version. But I've put these in here. You'll notice these are my double angle for trig. If you use any of these, you better use Osborne's rule to make sure that they are the correct version for the hyperbolic identity. So I'm going to use this one, and the hyperbolic version happens to be identical because of Osborne's rule. There's no implied one there. So cosh of 2x is 2 of cosh squared x minus 1, that bit there, minus 5 cosh x plus 4 equals 0. So that is just 2 cosh squared x minus 5 cosh x plus 3 equals 0. Oh, it's the same as the previous one, but with a 3, isn't it? So we get that cosh x is equal to 3/2, or cosh x is equal to 1. I'd like you to try and solve one of those in your head. Which is the one you can solve in your head and why? Cosh x equals 1. What's the answer?
0.
X is equal to 0, because you should know that the cosh graph looks like this, and it crosses at 1. So why bother using a calculator or a formula? You know that when cosh x equals 1, x is equal to 0. So x being equal to 0 is one of these things that we've got here. And that kind of makes sense because cosh of 0 is 1. So it's 1 minus 5 plus 4. It equals 0. So x being a solution makes sense. Now we're going to have a look at this one. So we're going to do x is equal to r cosh of 3 over 2. What is r cosh x? It's ln of... It's x plus x squared minus 1. Now, who can dig back to this time last week about what I said about what we talked about with r cosh? Yeah, something about... Yeah, so actually when you think about the graph, we're trying to say when is the cosh graph equal to 3 over 2? Well, that's about 1.5 there. So there are actually two solutions. And the two solutions will be symmetrical. So you can either use that knowledge that whatever one you get from here, you're going to have the same one but negated because it's symmetrical. Or we use the adapted version of this that has the minus. The reason it didn't have the minus and doesn't have the minus in the formula book was what reason?
When you draw the r cosh curve, it's to make it a function.
Good. Good. It was to make it a function because if it had this in it, it became a one to many. We couldn't do inverse function. We couldn't have the definition of a function. But remember, the formula book doesn't have it with plus or minus. If you're using it to solve equations, it will have a plus or minus. So we're going to do it both ways. We're going to do it with the symmetrical kind of pattern, and we're also going to do it with the using the formula in two different ways. So that means that x is equal to the ln of 3 over 2 plus or minus the square root of 3 over 2 squared is 9 over 4 minus 1, so it's just going to be 5 over 4. So x is equal to the ln of 3 over 2 plus or minus the square root of 5 over 4, which is root 5 over 2. So that's the ln of 3 plus root 5 over 2, or the ln of 3 minus root 5 over 2. So those are the two solutions. But didn't I say there were two ways of finding those two solutions? I said one of the ways was using this. But what was the other way I said that you could have found the two solutions? I talked about this on the graph. What did I say about this on the graph? If, let's say I found out what this one here was. Let's call that x1. The same one, but negated, should have been over here. But it doesn't look like that, does it?
It's because it's not the actual graph of
No, let's try and do what we did before, okay? Let's actually try and negate this. Let's just pretend this was the only one that we got, and now I'm going to negate this. So I get minus ln of 3 plus root 5 over 2. What does my log law say I can do with that, Araful? Put the power up to the top, power of minus 1. What does power of minus 1 mean? So it becomes 2 plus 3 over root 5. What do you think 2 plus 3 over root 5 is? I hope it is, otherwise this is broken. Because if you rationalize the denominator, you do get ln of 3 minus root 5 over 2. So even though I said at the beginning there were two ways of finding it, that you can either get the first answer and negate it, or you can use the formula in both different ways, they are the same thing. I just think it's kind of cool that you thought that isn't that one negated. Even when you take the reciprocal, you're like, oh, it's still not the same thing. And then you rationalize the denominator, and you do get the same thing as what the formula provides. I just think that's amazing. I just love seeing all these connections all together. Okay, we'll squeeze in one more question before the bell goes, and then you're going to try some practice. I'm not going to expect you to do all of these ones at home, because we're doing it like a lecture style today. But that was kind of cool, right? That there's the two ways of doing it. perhaps the way I would the one I would want you to do is I would prefer you to do this one, and that is usually because the question would ask for it as an ln of something. It wouldn't really like you to do it as a negative ln or something. But sometimes if they don't tell you how they want the answer, find one and just quickly whack in the other bit, okay? So we're going to just do something that is sort of related to this. It's not going to be the same as those equations. It's going to be to do with other identities, just pulling together lots of information that we've got here. So we've got if sin x is equal to 3/4, find the exact value of cosh x. Well, what links together, what identity links cosh and sin? Good. So to find out what cosh is equal to, cosh x is the square root of 1 plus sin squared x. Just rearranging that. So cosh x is going to be the square root of 1 plus 3/4 squared. And 3/4 squared plus 1 is 25/16, which is equal to 5/4. Why am I not going to take the negative square root? What would be the issue of writing this? Good. Cosh has to be bigger than 1. So you can't have cosh of x being something that's minus 5/4 because we know that cosh x is greater than or equal to 1. Do you see how this topic is just testing everything you know? It's not about learning something, it's about understanding everything that's going on here. Okay, so part B, we want to find out what than is. Well, I know what sin and cosh are, so how do I find than?
Sin divided by cosh.
Good. So I'm going to just do sin divided by cosh. So sin is 3/4, cosh is 5/4, and so than is 3/5. And then our last one is sin 2x. You won't be familiar with what sine of 2x is because we only introduced it at the start of the lesson, but it's one of the double angle formulae. Now we know that, if I just do this in a quick different colour, sine of 2x, can anybody just look from their notes what sine of 2x is? Yes, good. It's 2 sin x cos x. So for the hyperbolic one, is it going to be the same or different? The same, okay, because there's no implied sine squareds there. So if I want to find out what sin of 2x is, it's just 2 sin x cosh x. Good. So it's 2 times 3/4 times 5/4, which is 30/16 or 15/8. So they just want you to kind of pull all of these things together. Now, the equations, this allows us to now do up to question 9 on the exercise, but I just need to decide, I'm just going to stop it here and I'll decide what I want you to do for homework, okay?